Howdy, NRF 10. I'm going to take a look at solving systems of linear equations today, and um, we're specifically going to be solving linear equations that have just two variables in them, so linear functions like we're used to looking at. So the systems that we're going to be doing with these are sometimes referred to as two variable two equation systems. So there's an x and a y, those are your two variables, and we are going to be looking at two such lines at the exact same time, which is your two equation part. So, in solving these, there are a number of ways that you can look at doing it. There's graphing, elimination, and substitution, are kind of like your, I guess, your more normal ways of looking at how to go about doing these particular things. There probably are some others that are you could bump into as well, but these are fairly typical and worth looking into. Today I'm just going to focus on graphing and elimination. I'm not going to get into the substitution bit, so that will be for another time. All right, so this is what from a picture point of view, from graphs that are already given, systems of equations, which have two equations and two variables, look like. So the one that's on the left-hand side there, we have, sorry if you have difficulty with colors, but I have a red function and a blue function. It doesn't really matter which is which, so as long as you can see the two lines there, that's all that's really important. So sitting on my graph, I have these two functions. What a solution to a system it means, it has to be something that satisfies both lines at the exact same time. So all of these points satisfy that line. So any of those points is a solution to that line. Any of the points along here is a solution to this line here, this function if you wish. So if you were to plug in, for instance, a value of 1 into this function, it would give you a 2 as an answer. That is a solution to that linear equation. However, that solution of 1 comma 2 is not a solution to the other function, the blue one here. So if we want to solve the system as a whole, it has to be something that solves both of these lines at the exact same time. Now, from a visual point of view, that's pretty easy here because there is only one point that is a part of both this line and this line, and that's this point right here, 2 comma 1, which is the intersection of those two lines. So that's one of the things that can happen when we graph two of these lines. Now, this second example, you might not be able to tell. Desmos does a pretty good job, though. The blue and the red are actually overlap, so it kind of shows up a little bit purple there. So I actually do have two lines, but they are not distinguishable from each other, which means that if I looked at the point 1 comma negative 1, it would satisfy both of those lines. If I looked at the point 2 comma 1, it would satisfy both of those lines. This actually has an infinite number of solutions. Every point that works on the one of the lines also works on the other line. So that's kind of interesting. So basically, one solution, an infinite number of solutions, or this last example, we have two lines that actually have the exact same slope. So they're parallel. We saw that earlier where we talked about slopes being the same, meant that the lines were parallel. So if they are parallel, they maintain that same spacing forever, and they will never get closer and cross, and they'll never get farther apart either. But what we would care about is when there's a point on both this red function and this blue function that would give you the same value for the same x input. So basically the same point, like we said in the first example. That doesn't happen here. So because of that, there are no solutions to that particular system of equations. So you can have one solution, an infinite number of solutions, or no solutions. Those are all three very normal answers to a system of linear equations. Now, again, these are all picture examples of a 2 by 2 is probably what I'll refer to them. So 2 equations and 2 variables. A 2 by 2 system of equations. Now they're going to look a little bit different for, say, a 3 by 3. So in that case, you're talking about the best way to represent them graphically would actually be in 3 space or 3 dimensions. So you'd have this kind of like probably a 2D representation of that on a screen or something. But if you had an actual like 3-dimensional hologram box in front of you, you could run lines through that box, and of course you could solve systems of linear equations in that hologram as well. But that's, and the funny thing is, we can picture it in 2D, we can picture it in 3D, but you can solve 4x4 systems of equations. I'm not very good at picturing what that means, so I had one professor at one point in time, or somebody, maybe it wasn't a professor, that tried to explain how to picture a 4-dimensional type organization, and it was over my head. And another professor one time invited me into his office and showed me it was what I thought was a 3D model, but just like how 3D objects can cast shadows that are 2-dimensional, the argument is that 4D objects cast shadows that are 3-dimensional, and he was telling me that this thing that I was looking at was actually the shadow of a 4-dimensional object, and I didn't really understand. But that's all well and good because it's pretty interesting. From an algebraic point of view, multi-dimensional things are not too bad. It's all treated the same way, but from a kind of physical geometry point of view, my brain has a bit of a hard time with it. Luckily for us, 2 dimensions are not too bad to picture because flat screens are very, very good at being able to show what things look like in 2 dimensions. All right, so the single point solution is this option. Again, I forgot I had broken them up into different things. So here you go, single point. In this case, we have an infinite amount of points, and they are all along the line. So you could actually just say that the solution is that line, either one of them. Now, I say either one of them. Obviously, they are the same line, but they might look different in terms of the algebraic representation of them. So it's quite possible that one could be in even just slope point form, the other could be in slope intercept form, and you might not recognize until you go ahead and solve that they are in fact the same line. And in this case, there are no solutions. So this is all well and good. It's pretty simple to look at a graph and be like, yep, that one has a solution, that one has lots of solutions, and that one has no solutions, because it's staring you in the face from a picture point of view. So what if instead I were to give you just the equations that went along with that? What could we do? Well, one of the things we could do, oh yeah, and of course I forgot that I was going to do this, and let's see if I can actually get this in real quick. So, no, I don't want to go to that. I want to, yeah, I would had to import from somewhere else. So I'm just going to do a little freehand sketch. My apologies of how that might look on here, but we'll do our best. So this are my axes, and I am going to say that each one of these is actually 2 units. So I'm going to come out here, that's 2, that's 4, that's 6, that's 2, that's 4, that's 6, and which means that these are also the same spacing in the negative direction. Negative 2, negative 4, negative 6, negative 2, negative 4, negative 6. All right, so what I'm going to do from here is I am going to graph these 2 equations that are on the screen myself. So the first one is in slope point form, and I'm going to take advantage of that, and I'm going to graph by looking at the point that I can put down very quickly by reading it off of that form. So as a reminder, that form is y minus y1 is equal to m times x minus x1. So what we have already written down there is that there is a point that is x1, which is -2, comma y1, which is a 3. So -2, comma 3 is right here on my graph. And so there is one point. I also know that the slope is +2, which means if I go over 1 unit, I go up 2. On my graph, it's actually easier to see going over 2 units, I guess. So if I were to go over 2 units, that would be going up twice the slope of 2. So going up 2 and then another 2, which is 4. So I'm at a 3 right now. That would take me up to a 7, which would put me somewhere up here. So I'm going to take those two and play connect the dots and say that that is my linear function that's represented with that particular equation. So that was just putting down the one point that we knew from the slope point formula, and then using the fact that we know the slope to just make up another point. I went over, because of my scale, I thought it would be easier to go over 2 and not 4. As I said, if you went over 1, which would give you 2 right about here, you go up 2, which would be about right here, and we could have used that point instead and drawn your straight line through that, and that would have been fine as well. All right, so that's one of the two lines. The other line is y is equal to -x plus 1. So this is in slope intercept form. So I know that my y-intercept is +1. So this form is y is equal to mx plus b. And so my m, which is my slope, is -1, and my y-intercept is +1. So that would be a +1 for the y-intercept. And I'm going to choose a different color for my highlight. Let's go with orange. So we get kind of a muted orange there. That would be my y-intercept. And then I'm going to use a slope of -1, which means if I go over 1 to the right, I go down 1. I am going to use the kind of my half ticks here. So I'm up right now at 0, 1. So if I go over 1 to the right, I go down, and I'm on the x-axis. So that would be my other point here. Now, if I were to draw a line that goes through those. Now, the funny thing is that I'm freehanding all this. So one of the crappy things is I have likely put my half markings not exactly where they need to go, which is okay. But I might think from my graph that the reasonable solution to this appears to be that they will cross right there at that particular point. If I'm a little bit off graphing, that would be reasonable. If I'm actually been really accurate from a graphing point of view, then that means that this solution may not be very nice, and I don't know if I can find it very well by using a graph by hand like this method. If this was on graph paper, I would try to be maybe a little more careful. I mean, I have grid stuff on here, but my half markings are a little bit off, perhaps. And we would do our best to use a ruler and really make sure that those lines are as accurate as we can make them. Let's just say we think that that's the answer. So that would mean that our answer in this case is -2, 3, which is funny because it's actually the point that's given in the slope point form. Now, before I recorded this, I did this in Desmos as well, and I put it underneath of here. Now, I could also show you doing it in Desmos, which maybe I will in a second, but let's just take a look and see how it was. So this looks like at -2, 3, which is the point that we came up with. They do cross very, very nicely. Now, if you want to use a piece of graphing software to kind of see how you could do this graphically by using software yourself, one of the things that you may bump into is you can throw into Google like solve a linear equation, and then you just like plug some stuff in and it will solve it for you. this is a little, not better, but it's a little more kind of like you showing understanding of what's going on. So I'm going to switch this over. Actually, I'm going to switch it to Desmos and my iPad. So right below me is Desmos, www.desmos.com. I find it to be one of the nicest online graphing software, I guess, or applications that's out there. It does a really nice job of doing most of the high school stuff that I've been using it for. And anyway, it's pretty clean, pretty tidy. It formats your equations really nicely if you get things that are a little more complicated, so that when you go back to read your equation, it's really easy to understand without having to use 25 brackets. All right, now let's put in what has been given to us in this question. Well, actually, I did a bad thing. I'm going to switch back just real quickly here. So Desmos is now going to go over there, and then I'm going to use the equations down there in order to graph this. So I'm going to put in just the way that it's written. So y minus 3 is equal to 2 onto in a bracket, x plus 2. So one of the cool things is my caps lock must be on. I must have hit it by mistake. There we go. So one of the cool things is it does not need you to format your equations in any particular way. So that one is in slope point form, and it's fine with that, no problem at all. The other one I'm going to put down is y is equal to negative x plus 1. And so you probably can tell that the image that's over here, I originally had made it in Desmos myself, and that's where this comes from. And we can also click, which is pretty cool. So I can make the lines a little thicker for projector mode there, so we can see a little better on our screens. And negative 2, 3 is definitely the intersection point. I can click on it and make sure. And so, yes, that is the solution to our problem. So, basically, as long as you're good at graphing from the last stuff that we were doing, you can solve systems of linear equations, especially if the numbers are pretty nice. So this one went right through a nice grid point. That's great. So it solves really, really well. Now, if it doesn't, which from my freehand, I don't know. It's a little bit sketchy for me to just say, yeah, of course it goes through negative 2, 3. It was close, but maybe a little bit off there. If I'd done a better job, that might have been a little more convincing. Desmos does a very convincing job, so that's not a problem there at all. And actually, if you're using Desmos and not doing it by hand, the issue that's down on that screen is not going to come up anyway. So it doesn't really matter if it shows up on a grid line. So I'll show you what I mean by that. So if I am to increase that by 1, so it's just negative x plus 2 instead, you'll see that the intersection point there is now kind of floating in between grid lines. By hand, that's a pain in the butt because it's really hard to say that that's exactly at 2/3, so that's negative 1 2/3 and 3 2/3. But algebraically, it's actually quite easy to show. So we're going to look at how to do this algebraically as well. So here we go. Elimination and substitution are both algebraic methods, and they're going to allow us to get solutions to these systems of equations as well. One of the nice things about them is that you don't come up with that particular issue. I would like you to be able to graph linear equations and be able to see that the solutions can be read off of those. What your solution sets look like for the one solution, no solutions, or infinite solutions. It's just good to kind of understand from a picture graphing point of view how things are behaving. All right, now I'm only going to do elimination right now. There is, I'm going to do substitution, I believe, next week. And yeah, so elimination, here we go. This is going to look kind of weird because probably not what you are expecting to see right now. So I'm going to switch back to being able to see my iPad, just in case I want to write some stuff down here. So the first, these are two balances. So they're going to tell you the weight of these balls that are sitting on top. And again, a color coordinated them, so if that's an issue, my apologies up front. I had someone that I taught that was colorblind a few years ago, and she kindly informed. I taught her in 2 different years, so grade 11 in physics and grade 12 in math. She kindly informed me in grade 12 that she was colorblind and that I'd done a whole bunch of stuff probably the year before that she couldn't really follow a whole lot, because I'm like, yeah, the red one, the blue one. And it wasn't real helpful. Anyway, no, it might not have been red and blue because colorblindness has. Anyway, well, that's for another time. All right, so green and yellow. The green ones are the ones here and here, and I have 3 yellow ones in each case. So these two balances are reading 11 pounds and 17 pounds. Now, you might be saying, what does this have to do with linear systems of linear equations? And I understand that that does probably seem a little bit weird. But the idea of elimination is going to be really, really clear in this particular case. So this is equal to 11, and this is equal to 17. Now, what would happen if I took off that much from this scale? Think about that for a second. And then I'm going to give you a big hint. That's my first big hint. It's my second big hint. You might notice that the stuff inside of those two ellipses or ovals or whatever you want to call them is the same. So how much does this weigh? It weighs 11 pounds. How much does this weigh? Well, that weighs 11 pounds too. And if I took it off of this scale, what am I left with? Well, I'm left with these things. And I'm left with this minus 11. So the original weight there was 17 pounds. But even though I didn't know that on the right-hand scale, by using the left scale, if they're all identical. Oh, so I didn't start off this problem very well. If I told you that the yellow ones are all identical and the green ones are all identical, but there's no, they're not necessarily the same as each other. So they might be, but the yellow and the green may have different weights. But they all have the same weight as the same color. So 17 pounds, and I'm going to take away 11 pounds worth of stuff. What's that leave us with? 6 pounds. And what's left are 3 green balls. And each one of them then is going to be 6 divided by 3, which is 2 pounds each for green. And then we can start doing things kind of backwards. I can take the smaller scale on the left and say, oh, well, if each of those green balls is 2 pounds, then I have 8 pounds of green balls. If I take those all away, I have 3 yellow balls that are left there, and I have 11 minus 8 pounds of balls on that scale. So I have 3 yellow, and they're equal to 3 pounds. And so that means that each yellow is 1 pound. Now, why can we do that? We can do that because this collection of stuff that we don't know is equal to 11 pounds. And this collection of stuff that we don't know is equal to 17 pounds. So those are equivalent things. And because of that, if I take away this amount here, it's the same thing as saying I'm taking away 11 pounds. Now, again, you might say, what the heck is he doing this for? Well, I'm doing this for this. This is actually the exact same case that we were just talking about. So it's a little harder to see because this is actually the one that we've already solved. This is our I think the answer was negative 3 comma 2. It was on the graphing one that we just did. I could go up here and check. So yes, negative 2 comma 3. No, I mixed them up. So we expect to get that same answer here. However, first of all, this is like a balance. So I'm going to multiply out the right-hand side and make it look like this. And then this one is like this. What is the balance in this case? Well, it's kind of like this equal sign. So this thing over here is equal to this thing. Great. So if I wanted to, and I'm going to rearrange that top one. I'm going to add 3 to the left-hand side, which means I add 3 to the right-hand side. So I get 2x plus 7. And my other one is y is equal to negative x plus 1. Now, I can add or subtract either one of these balances. And what I mean by that is, I have right here that I have y of these is equal to that. But I could subtract this y from that y. So it's like taking the balls away. But I know that this first y is equal to 2x minus 7. So if I subtract this y here from this y here, then I have to subtract this stuff from this stuff. Because just like we did here, where you took away this group of balls that was 11 pounds, well, we subtracted the balls in both, like in this case over here, we subtracted the 3 yellow and the 4 green from the big pile, but we also subtracted the 11 pounds from the 17 pounds. So this is like one side of our equation, and this is the other side of our equation with the 11 and 17. Over here, I have one side of my equation, and I have the other side of my equation. I'm going to subtract, and I'm going to label my equations. So I'm going to label this one as equation 1, and this one as equation 2. And I'm going to say I'm going to subtract equation 2 from equation 1. So on one side of the equal sign, I subtract. What happens here? If I take 1 and I subtract 2 from it, it's y minus y. Y minus y, which gives us 0. It's still equal to, because I'm doing this operation on one side of the balance, one side of the balance. So just like over here, where in the end I read that 3 green was equal to 6 pounds, I now have 0 as my left-hand side is equal to, and in this case, it's going to be 2x minus negative x, which gives us 3x. And then I have 7 minus 1, which gives us 6. So I can then rearrange that and end up with an x of minus 2, which is really good because that's what we were supposed to get. And then I take my answer and say, oh, just like last time, I had to figure out what the yellow balls were afterwards. So right now I have my x values, but I don't know what my y values are. How do I do that? Well, I go back up to one of my original equations that I have, and I say, well, I know that the x is actually minus 2. I'm going to use equation number 2, and it says that y is equal to negative x, which is negative 2, plus 1, which means my y is equal to 2 plus 1, which is 3. So I get negative 2 comma 3, just like we did in the graphing part. It's the exact same process. So what you actually want to do in an elimination type problem is you want to take away or add things to both sides of one of the equations in order specifically for all of the green balls or all of the yellow balls to go away. So in our context, that means we want all of the x's or all of the y's to go away. Now, I took this problem because it was a fairly nice example. If this didn't work out nicely from a graphing point of view, like on a nice spot, like the one that we have up to the right. So if I made that small change to it, not to the right, on the graphing thing that I did earlier, which is actually right here. If I use this set of equations instead, you could try those out. So you could pause and try those, and you should get this as your point if you do it. So you should get a fraction for both the x value and the y value. So that would be negative 5/3, and this one would be 11/3. And so if you get those, you're in really good shape, or you could get decimal values, and that would be okay too. All right, so the three types of solutions still show up here. Wow, English, 2 with 2 O's. All right, so still show up here as well. Now, what do they look like? Well, we just saw what happened if you have a single solution. You get a single number for your x, and you plug it into the other one, you get a single number for your y. So you get a point. That point is your answer. That's the single point solution. If you get something at the end that is like 0 is equal to 0, you're like, yes, it is. When is 0 equal to 0? All the time. So that would mean that any x value or any y value will be okay. Now, that doesn't mean that anywhere in all of 2D space is an answer. What it means is that you can find the line, basically, and any x value along that line is going to have a paired y value that is also an answer, because it's the same line overlapped. So you'll get something that looks like 0 is equal to 0, or maybe 2 is equal to 2. It doesn't have to be zeros, but you're going to get something that is true all of the time. And then if you get two parallel lines that go like this, and you try to look for a solution, when you simplify it, you're going to get something like 1 is equal to 0. And again, it doesn't have to be 1 and 0, but it's going to be something that's nonsense, that never can happen. And if it can never happen, what does that mean? There's never a solution. So works out nicely. You get some numbers. Great, one solution. Gives you something that's kind of nonsense, but in a always true way. So 0 is equal to 0, and you're like, duh. Well, that means you have an infinite number of solutions. And 1 is equal to 0. That can't ever happen. So no solutions. That's probably good for now. I am going to... if you want to stop, that's great. If I'm going to just run through the little problem that was right here on the screen, where I changed the variables just a little bit, and I'll show you how to get that negative 1.6 or negative 5/3 and positive 11/3, if you care about it. So again, if we just go ahead and, do you know what? I'm going to do it. No, I told you should do that one. I'm going to do that one. All right, so let's do it. All right, so same thing. I'm going to tidy up the first one so that it looks... I'm going to add 3 both sides and multiply out the bracket, so it looks a little more like the other one. So when I add or subtract them together, it makes some sense. So 2x plus 7 and y is equal to negative x plus 2. So in this particular case, if I subtract equation 2 from equation 1, you want to make sure, now this is why, do you know what? I'm going to do this a little different. You might think that this is weird, but I'm going to eliminate the x's instead of eliminating the y's. And the reason why is you should see that you are entirely okay to eliminate the other variable if you wish. So in that case, I don't want 1 negative x. I want 2. So for my second equation, I'm going to say negative 2x. And how do I get that negative 2x? I have to multiply everything by 2. So if this is a balance and I double up my y, so I have 2y on one side, I double up my other side as well, because I have twice the amount of stuff. So I have negative 2x plus 4 instead of the old negative x plus 2. Now I could take equation 1 and 2, and this is kind of a little bit different than the balances, because we don't have negative things when we talk about balances, so you'd always be subtracting. In this case, I want to add because I have a negative amount, and I want to get to 0 of the x's. So if I do that, I'm going to have 3y is equal to 0x plus 11. So our y is equal to 11 over 3, like we said it should be. And then if I wanted to check and see what the x values were, I could put it up into either one of my original equations. So 11 thirds is equal to 2x plus 7. So 11 thirds minus 21 thirds. 7 is the same thing as 7 over 1, the equivalent fraction, multiplied by 3 in the numerator, multiplied by 3 in the denominator would be 21 over 3 is equal to 2x. So that would be 11 minus 21 would be negative 10 over 3 is equal to 2x. Divide both sides by 2. The negative 10 would divide by 2 and give me negative 5 thirds, which again is what we said we should get and is still sitting on the screen if we want to check it. So that's negative 5 thirds, and this one's 11 thirds. So our point would be negative 5 thirds, comma, 11 thirds. All right, so that is how to do some elimination. I might do a couple more examples and upload them so you can see some more if you wish. But for now, I think that's good. And I have a class in 2 minutes, so I probably should get skedaddling over to that. But I did want to do that second example where you can see it works with fractions really well, even though if you had done it graphically, it would be a little bit sketchy to know that it lands right on that point. So I hope you're doing well. Take care, and I hope this is Thursday when I recorded this, so I hope to see some of you tomorrow. Take care.